Hey guys, this is Mr. Larson. Today we're going to go through 1.4 notes. Today we'll cover determining if relations are functions with a couple different tests. Then we'll talk about evaluating a function over different inputs. And then lastly, evaluating the domain of functions. So a couple definitions. A relation is just very simply a relationship between inputs and outputs, x and y. And if an English teacher were here, they'd yell at me for using the root word in the definition. But you know what? I ain't no English teacher. Okay. What is a function? Well, a function is a special type of relation. Every input has no more than one output, which I'm sure you guys remember from Math 1, which I teach Math 1, so I know that that's taught in there. Okay, so let's talk about three different, these aren't the only three, but three different expressions of a relation. So you could have a graph, a table, or an equation, right? You could also have words, some other ones, but those are the three that we'll talk about today. So looking at a graph, we can do the vertical line test. And if you remember, you can hold your pencil and kind of slide it left to right. And if your pencil, holding your pencil like this, if your pencil ever hits the curve in more than one spot at the same time, it would not be a function. So this parabola, no matter where I put that vertical line, that pencil, it's going to cross only once, at most once. So yes, this is a function. A circle, this is one of the most missed ones. A circle is definitely not a function. As you can see, that vertical line is hitting in two spots. Okay, so don't be one of those people that on your quiz or test, wink, wink, there is a question about that, perhaps, that thinks that a circle is a function. It is not a function. Okay, here's some other relations, and we need to determine if they are functions. So the first one here, 1, 2, 2, 3, 3, 8, 5, -3, that's just a list of points, right? And we can put that into kind of a table type view. It's called a mapping. So we draw one oval with our inputs, and we list them in increasing order, and we don't repeat any numbers. So 1, 2, 3, 5. And then we list our outputs the same way, lowest to highest. So -3, 2, 3, 8. And then we simply map the inputs to the outputs. So here's my inputs, my outputs, 1, 2. So 1 goes with 2, 2 goes to 3, 3 to 8, 5 to -3. And what we're looking for here is if there's two arrows originating from the same input going to different outputs. And none of these inputs have two arrows coming from them going to different spots. So this passes the test. Yes, that is a function. Okay. Eventually, you can probably just look at the points, the x's and y's, and figure it out. But I'll set up a mapping again for this one. So we have 2, 3, and 5 for our inputs. -11, -2, 4. Oh my gosh, what happened? 4 and 5. It's really awkward writing on this tablet, so you guys will just have to deal with it. All right, 3 goes to 4. 5 goes to 5. 3 goes to -2. 2 goes to -11. So if you guys see right here, this 3 has two arrows coming from it and going to different spots. So that is not a function. That input has two outputs. Okay, so not a function. Okay, this third one down here, you could list these all as points and then do a mapping just like we did on the previous two. Or since it is represented graphically, you could also do your vertical line test. Not all graphs have to be continuous, like where these are connected. You can simply have these 1, 2, 3, 4, 5 points, right? And we can see as I move from left to right with a vertical line, it's not going to hit any of those points more than once. So yes, this is a function. Okay, so that shows you can do vertical line test here, or you can come back and do something similar to this and just list out all your inputs and outputs again. Okay, determine whether these are functions or not. I'm not going to go through those. You can look at the key and at the examples that we just did. Okay, so here's a couple more examples. Y equals the absolute value of x. We're going to determine these by an input-output table and then also by sketching a graph. Some of us might know what the absolute value function looks like. It looks like this. And let's do a quick table here. So x and y. Let's see. Let's do some negative numbers. 0, -1, 0, and 1. Okay, when I input -1, absolute value of -1 is +1. When I input 0, absolute value of that is 0. When I put in +1, absolute value of that is +1. So we could see if I went in either direction, I plug in -2, I'd get 2. I plug in +2, I get 2. So every input has exactly one output, right? It's plugging in -1 is never going to give me anything other than 1. So this would be a function by definition. And also we can see from that graph that that is going to pass our vertical line test. Okay, x equals y squared. I believe you guys should know what that graph looks like. That's going to be a sideways parabola in the positive direction. And let's see, quick input-output table. Let's plug in 0 and let's see what I get. So y squared equals 0, square root both sides, and I get y equals 0. Okay, let's try 1. Y squared equals 1, square root both sides. Remember, when we square root, we need to take plus or minus. So that didn't really apply when it was equal to 0, but now it's going to equal y is equal to plus or minus 1. So when I input 1, I get 1. But when I input 1, I also got -1. So you see how this input generates 2 outputs. And that is not allowed. It also doesn't pass the vertical line test. So this would not be a function. First one was yes. Second one is no. Okay, let's move on. Evaluating a function using function notation. These are pretty easy, but just to recover or just to refresh you, y equals 2x plus 1. Let's rewrite this in function notation. So this y becomes f of x. We said this is a function of x, and the rule is 2 times whatever our x value is, and then we add 1. So let's evaluate this. So f of x becomes f of 1. So the x turned to a 1. So over here, I'm going to turn x to a 1, right? So it's 2 times 1 plus 1. That gives me 3. When I plug in -3, -6 plus 1, -5. And then we can plug in an expression here. You don't always have to plug in simply a constant, right? It can be something other than just a number. So the same rule is going to apply. Instead of 2x plus 1, it's 2 times your input plus 1. So I have to distribute here. I get 2x plus 2, and then I have that plus 1. This gives me 2x plus 3. And those tend to be the hardest ones because we don't like to see something other than just a nice constant, right? X plus 1 includes a variable plus some other stuff in there. So I'll let you try number 8 there. You can check the key, and then we'll move on to determining the domain. All right, so taking the domain of a function seems to be one of the more complicated things in chapter 1 for some students. So The one thing I always try to remind my students is that whenever you go into a problem and you're finding the domain, when it's written as an equation, as a function, assume that the domain is all real numbers, right, with no restricted values. Then see if these two scenarios apply, and you can start taking numbers out of the domain. So we assume that it's going to be all real numbers, and then the instances where it's not will follow one of these two. So if there's an x or your variable in the denominator, then you might have some restricted values because, of course, you can't divide by 0. So any values of x that make the denominator 0 have to be removed from the domain. The other scenario is if x or your variable is under a square root, and technically it's any even root, but for all intents and purposes, let's call it a square root, which is your second root. That generates some restricted values because you're not allowed to take the square root of a negative number. So any values of your variable that generate negative values under the root have to be removed. Okay, so let's take a look at this. What happened here? Okay, so number 9 here, f of x equals 1 over x plus 3. Well, I have an x in the denominator, right? My denominator is not allowed to equal 0. So subtract 3 from both sides. I can solve this just like an equation. X cannot equal negative 3. So if we remember our interval notation, I can be every number from negative infinity to positive infinity except for negative 3. So that would be negative infinity to negative 3 union negative 3 to positive infinity. Okay. Okay, number 10 is similar. I'll let you guys try that on your own. Number 11, I don't have any of these scenarios. I don't have an x on the denominator. I don't have a square root. So this one is going to be all real numbers. 12 and 13 are a little different. So for number 12, f of x equals the square root of x minus 7. So now I have this scenario number 2, right? I have an x under the square root. So I know that the value under a square root, which in this instance is x minus 7, has to be positive or it's got to be 0. So we can say it's got to be greater than or equal to 0. It can't be less than 0 because then I get an imaginary number. So by adding 7 to both sides, I get x must be greater than or equal to positive 7. And switching that to interval notation, I would have bracket, because I'm including 7, up to infinity. By the way, some of my students get confused by how do you remember if it's a bracket or a parenthesis. If you can equal that first number, then it's a bracket because you can't draw your bracket without this equal sign, right? So that's kind of how I remember. If you're including that number, if it can be equal to that number, then you would use a bracket. So from 7 to infinity. Okay, 13. So this one, wow, this is interesting. I have, let's see, on the numerator, square root of x. So that's scenario number 2 up here. And then on the denominator, I have x minus 1. That's scenario number 1. So I have to think about 2 different things. Okay, let's just do these individually. So the first one, the value under the root has got to be greater than or equal to 0. So x has to be greater than or equal to 0. Okay, that's manageable. Down here, I know the denominator can't equal 0. So if I add 1 to both sides, I get x cannot equal positive 1. So how do I express that? Okay, greater than or equal to 0 and then can't equal 1. Well, from this first part, if the only restriction was from the numerator, do we agree this would be from 0 to infinity, right, with a bracket on 0? However, I need to take out a number. I need to take out 1. So this actually changes into, when I think about this other restriction, okay, I can be from 0 up to 1. I remove it, and then I continue all the way to infinity. Okay? All right, guys. Thanks for checking in, and we will see you next time.